Thank you so much for checking out another episode of the Weaviate Semi-Technologies podcast. I'm here with Bob Van Light, CEO and co-founder of Semi-Technologies. Me personally, Bob has told a story that has really captured my interest in the Weaviate vector search engine. Listening to his storytelling it on Dimitri Khan's Vector podcast and all the different YouTube videos on Weaviate has really captured my attention and caused me to be really interested in vector search engines. So I'm sure that this, another edition of listening to Bob tell the story will help you also be further convinced of how exciting this technology is. So as we do this podcast on the Semi-Technologies YouTube channel, we're sure most of our listeners are already pretty familiar with the basics of vector search engines. If you're not, there's an introduction to Weaviate on Semi-Technologies. I've made one as well on Henry AI Labs. There's all sorts of resources to get caught up with the basics. We're going to kind of go into the details and flesh out these visions for the future, these exciting ideas like GraphQL, knowledge graphs, neurosymbolic search, these recent advances in information retrieval and supervised learning, multimodal learning like image text search, the demo endpoints, the demos, and how we see that playing out. All sorts of really exciting things going into the research and the future and all these kinds of exciting things. So with that said, I think the first thing to talk about will be what is your vision? How did you think of this GraphQL knowledge graphs? Because I think this is a really unique flair of Weaviate that I don't see out there a lot.
Well, yeah. First of all, thanks for having this conversation with me on our own podcast, I guess. But So originally the idea came from the fact that I was very intrigued by everything that had to do with the semantic web and those kind of things. And if you deal with the semantic web, then you're very quickly into the space of ontologies. And there was this one thing in when I went to conferences, when I spoke to people, that just fascinated me. And that was that if we talk about the definitions that we have in ontologies, is that people don't agree on things. It's just, that's something that fascinates me. And this is causing a lot of problems, right? So because if we want to search through specific data sets, or if you want to find something, then that's hard to do. And I once gave a talk in Greece, and there was like this guy, and he said and he was upset about this as well, because he said I'm working for the European Union and I'm tasked by creating the ontology for rivers, lakes, and seas in Europe. But he said, you know what the problem is? I said, tell me. And he said so what the rest of Europe calls a lake, they call a sea in Germany. I said so we couldn't agree. So he said I delivered the ontology, and then the people in Germany said no, that's not a lake, that's a sea. And so this was a constantly occurring problem. And if you see public discussions related to Wikidata, etc., you see that this is a constant problem. So then I got introduced to everything related to vectorization and NLP. Bear in mind, I'm not that old, but it's this is before BERT and transformers and that kind of stuff. And I remember that the first thing that I saw, that it was that famous example, I believe that it was king minus man plus woman and then queen, that result. That was the moment I saw that for the first time, I was boom. I was wow. And a few years later, I got this very simple idea, which is a very hacky idea, right? But I got this idea that I said what if I just have a bunch of documents, just 3 documents, or a paragraph of text or something. I just take the individual words and I just calculate a centroid of all the individual vectors of this of these paragraphs. I just wrote that in Python, so it was really slow. But the goal that I had back then was just to figure out can I find that document by searching for context rather than for keywords. And when I was able to do that, I was I had this thing that was boom, this is an opportunity, because now we can target a node in the graph without knowing what the current ontology is or the keywords are. We just have to describe it, and then we can find it. And from there on, we can traverse the graph. So that is what the original idea was. And there's way more to say about this, but we'll probably touch upon this. Related to GraphQL, that's another thing, because I am a very, very strong believer in a developer user experience. And now you have a problem if you're dealing with a graph-like data model. And the problem is this. So how much flexibility do you want to give the end user to traverse down this graph, right? So do you want to be super expressive, then something like Sparkle is interesting? Or do you want to be less expressive, but give a lot of, make it easier to use? And then we of course have something like GraphQL. And just asking developers about their what was very intuitive for them and what how they wanted to use the interface, we actually learned that a lot of them liked GraphQL. And that's also what I see when I give demos. I sometimes say it's GraphQL, and if people say like I never heard of GraphQL, I say like don't worry, because I'm going to type it out and it's going to be intuitive. And plus the fact that we are not a graph database but really a vector database, we said like we don't have to support all these specific graph things like Neo4j does or dgraph does. That's for them to solve. We have this graph-like data model where we want to target these nodes, and we're going to use GraphQL to do it because we believe that is the easiest way for people to use it. So that is the history of that interface. I have to say that was just the concept. The actual design is done by my colleague Laura. And there's also some videos from her online and that kind of stuff where she explains what she did there. So credits for the design go to her. But the overall concept was like, how can we give the best UX to end users to get access to these vectorized data objects?
Yeah, and I think one of the like visualizations of vector search that we like the most is say image search, like where we say take fashion MNIST and we go find the nearest looking bags, but that's missing the metadata of the underlying image data. And so having that metadata and then using the graph syntax to be able to traverse it is something that I think is a very exciting visualization. And yeah, the GraphQL demo, the semi-console, it's a very cool way to start playing around with vector search engines. And something that I'm also working on is like a tutorial on using GraphQL, but generally it's pretty easy to get started. And Weaviate has at least 15 examples on the documentation for anyone out there looking to get started with GraphQL. And again, Wikipedia, Wikidata, and also news articles are up there already if you wanted to start playing around with GraphQL. So to backtrack a little bit, you were talking about text embeddings and graph embeddings, and this idea that you would use the, say, average of a paragraph about seas and lakes in Greece to get a text embedding, and then go hit the semantic web graph. And I was recently talking to Charles Pierce at Kenius about how they have this scientific literature suggestion where you highlight some text and then it goes into the knowledge graph of a citation network. So is that the vision, that you start off with a text embedding and the text embedding takes you into your position of the graph, and from there it's about traversing a knowledge graph?
Yeah, so the original idea was a little bit more abstract. So the original idea really was like, how can I target this data object in the graph without knowing what's in it? How can I solve that? And that is what the embeddings solve for me. That can be text embeddings, but that can also be, as you mentioned, image embeddings and those kind of things. What's also important to bear in mind is that I came from somewhere else, as where, for example, data scientists come from. So a data scientist might come from, hey, this is really cool. We can build a recommendation engine. So I'm going to take MNIST, etc. I really came from the engineering / database perspective. So like, how can we build a database that is just smarter, air quotes, in storing data? So it was a completely different approach. And that is, for example, why I love the case of Charles and Kenius so much, because that is that idea in action. So they're using that exactly. So you have a database that makes it easier for them to search through to the content. So it's a little bit of a different point of view. And the embeddings are just, and I have to be honest, here we're just also a little bit lucky, right? So with everything that's happening in research, because we're now often talking about image or text embeddings, but we're looking at use cases for cybersecurity embeddings, healthcare embeddings, you name it. And you can store all these embeddings, including the metadata in Weaviate. So I really think that the coming 1-2 years, we're going to see so many cool use cases from stuff that people are creating embeddings of. So that's going to be, that's just going to be amazing.
Yeah, and we'll definitely get more into all these different use cases and the multimodal. And personally, I'm working with the Memorial Healthcare System data, where we have convalescent plasma therapy treatments for COVID-19. and we're trying to do this kind of vector search where we're looking for patients. And it comes back to this topic that we're talking about, where you have an underlying symbolic schema and this kind of idea of neural search and symbolic search and the way that you really want to do neural search. So a lot of the times, and Charles and Kenius outlined this really well with this concept of serendipity, and I hadn't heard this term before, and I think this really describes it. If you do a text embedding, the result that you get might kind of confuse you compared to a regular expression matching. So if you search for keywords, or like whatever search you do, you're going to expect the keywords to be in the result, kind of. Like, it's just kind of, I think, how we're biased to use search engines given Google and just our experience with this technology of search engines. So I think we're still generally getting used to this neural search and symbolic search. So Weaviate is a neurosymbolic system. I think one of the most applicable neurosymbolic systems that have come to exist. So is this something that this neurosymbolic kind of categorization, do you think this is something that motivates and trading off symbolic queries as well as this neural search? And how do you think about those two kinds of searches?
Yeah, so first of all, I love that example because I'm dealing with that as well. So just for some context, so what am I doing like mostly on a daily basis? I'm helping users and talking to users like, how do you use it? And one of the things, the patterns that I see is that, of course, people have like a status quo search engine that they use, and then they move to something new. And indeed, keyword search is very binary in its results, right? It's true or it's false. So if you search for Apple and it shows you an article about toothpaste, then you go like, that's just wrong. It's you can like in a binary fashion, like, okay, there's something wrong with this thing because I search for Apple and I get toothpaste. That's of course different when we're dealing with a vector search engine, because now we just search for something in the vicinity of something. And the interesting thing was, I was talking to a researcher who's doing a lot of work in this space, and I like a year ago or something, I said like, how do we know? And he says like, well, intuition, right? So if I type in landmarks in Paris and I happen to have a document about the Eiffel Tower and it returns the Eiffel Tower, then it's our human intuition that says like, oh yeah, that makes sense. So one of the things that we're playing with is that we're saying like, well, we are returning, of course, in the results also the what we like to call certainty, which is a little bit of an algorithm. It's a very simple algorithm, like how to determine based on the distance. You can also return the distance. We're also going to work with different distance metrics. And then you can say something about, for example, cutoff points in the distances where it's probably a relevant result. So that's the first part of my answer. The second part of my answer about keyword search, that will definitely play a role. I have an example on the in the demo data set, in the Wikipedia demo data set. Where we deal with named entities. So I often like to take music examples. So I believe that the question that I have there in the demo data says like, what was Michael Brecker's first saxophone? Well, if you run that query, you will get the answer, but it's like on the third or the fourth result. And there's just one right answer. So what you can do is you can mix in the where filter on the named entity that's in there, Michael Brecker in this case. So you still have the semantic query, what was Michael Brecker's first saxophone? But then you only say in the where filter, this must be related to the keyword match Michael Brecker. And then you still get the right result. So what we see happening a lot is that people start to mix in these named entity recognition things, where they say like, hey, if the query contains a named entity, we're going to do a scalar search or just a where filter search in our case on that named entity. And the rest of the question, we're going to match based on the semantics of the question. Really depends on the use case. The third thing that I want to say about that is about that word serendipity, because I love that word as well. What we see from that point of view is that people come up with a lot of very cool creative ideas to actually use the serendipity to their benefit. An example is this. So what I did years back when I tried this out with creating centroids on the individual words, we now see people do this again, for example, in e-commerce. So let's say you have 100K products and they all have individual vector representations that they got, for example, from a sentence BERT embedding. So they have these embeddings, models. So they have these sentence word embeddings to them. And now somebody adds something to their cart. So 3 products to their cart. What you can actually do is in Weaviate, you can say, I'm going to take the 3 embeddings of this product in that cart, and I'm going to represent the user based on the centroid of these 3 embeddings. So now if somebody searches for something else, you can bias the result towards the centroid of what's in their shopping cart. So if somebody has, so we are about to release an e-commerce demo based on this. So if somebody has like all kinds of sporting wear for like women's sporting wear in there, and then somebody searches for a jacket, then you can actually bias the results to, for example, women jackets. Or if somebody has a lot of things related to yoga in there, and then you search, for example, for ball, then you can actually show yoga balls first before showing soccer balls and those kind of things. So that is an example of where that serendipity is actually used to improve the results and and create better search engines for whatever use case people have.
Yeah, that's such an interesting, like another way of looking at the serendipity thing is the biasing it with the nearest neighbor to filter the search. And I think generally for everyone listening, I'm sure a lot of our listeners have heard about this yet, but what makes a part of these vector search engines so different from, say, just running your data through your neural network and then taking the embeddings and putting them into memory and doing some comparison is there are these data structures like the centroids Bob is describing that speed up these searches. So HNSW is a graph that traverses these centroids to help you find nearest neighbor vectors. So you don't do order n, compute go through the entire vector set to compute the distance with every one, which would be impossible for massive documents and all these kinds of things. So that's a really interesting idea, the serendipity of you bias it, you say, I want something that's kind of similar to this. And then the HNSW graph can be like, okay, great. I've already built up this index that already helps you do that kind of filtering. So then coming back, the idea of the human intuition that helps us interpret these results. And so another kind of topic, and I love the idea of these user interfaces for human intuition, things like, as you mentioned, the certainty that gets returned at the neural search is, I've personally uploaded my Keras BERT data set into Weaviate, and I've been playing around with searching for nearby code snippets in the Keras code examples, and having that certainty that matches it and tells you it's 72% or 0.72% as you go down and you see the certainty, that really does improve the user interface, and it helps you feel more like, okay, I'm getting more of a sense of how this is working. And yeah, the named entity tagging, I love that idea because you can have like the keyword filtering on. To come back to the Keras BERT example, people out there are familiar with Keras. It's a library for deep learning. You might want to have it tag entities like use the attention layer if you're searching for implementations of new transformers. So that attention layer is like in a named entity layer of the Keras. So then kind of a big topic to come out of and then start talking about is going from human intuition to computer intuition and this idea of information retrieval and supervised learning. So I think you were really ahead of this and thinking about this early on with just the modularity and the building in of the question answering modules. So what was your thinking early on with the modules, and how are you thinking generally about this kind of adding the supervised learning modules functionality on top of vector search?
Yeah, so that's a great question. Thank you. But so one of the things that I was doing is that I knew from the work that I was doing back then. So I'm basically helping people to build systems for whatever they were trying to solve. Was that I knew that if we would be working on a database, that, as I always like to describe it, is the distance between the problem that the database solves and the problem that the end user needs to have solved. There's a gap between there, because a very simplistic example is people don't directly connect their app or their front end to Weaviate, right? There's always a piece of middleware that does something for their use case, like you do with any database. That's not different with Weaviate. So, what I thought about is like, so what can we do to bridge that gap, right? So how can we bridge that gap? What kind of things can we release? What kind of things can we make to that? And the modules are an example of that. So that we said like, well, if the majority of people are using, for example, sentence transformers, why not have a modular infrastructure to actually just offer that to people? And likewise, when it comes to for example, the HNSW plugin, which this year the credits go to HN for that idea. But there's like, Probably we will see others in the future as well, besides HNSW. So let's already be prepared that we can just change it and swap something else in. So it's more like from the inside out, and I'm looking from the outside in to Weaviate. And that's where the idea comes from. And now the cool thing is, Connor, and that is, well, I can use the word serendipity again, that we have one like power user who's like, hey, wait a second. We have like hundreds of models that we use. Can we actually automatically in the Kubernetes cluster spin up and shut down these modules around Weaviate whenever we need them? And we're like, yeah, sure, you can. So now we see these new use cases where people start to intertwine the ML stuff with the DevOps stuff and create these super huge systems where these models pop up, shut down, and what have you, all thanks to the modular infrastructure that we have. So I think that's that's just amazing to see. And again, to recap this, the goal here is to bridge the gap from the database to whatever the problem the end user is trying to solve.
Yeah, and that modularity connects to sort of the champion open source, the Hugging Face models, and it's such a nice modular integration. And yeah, you can just switch out the modules. If you have a question answering system that's going to be performing the task, you can just swipe it out with Hugging Face. And Hugging Face is really great to upload your models to. Just as a personal testimony to it, it's really nice to train like a language model, push it to the model hub, and then you can have the mass demo. Now they're building out Hugging Face spaces. They've acquired Gradio. They're really building this demo interface, and you can take all these models and plug them into Weaviate. And the modularity of that is so exciting. I love the modularity of how you can swipe out all these different components.
I agree with you. And what you see is like not only this, like, because absolutely, yeah. So the Hugging Face platform is fantastic, and we benefit from that as well. So that's great. But let's also not forget like platforms like Docker Hub, for example, right? Mm-hmm. So every time somebody downloads, we're slowly approaching 600K downloads, by the way. But that's thanks to the Docker platform. So Hugging Face, Docker, Kubernetes, of course, we benefit from these platforms. So that's just fantastic that they exist.
Mm-hmm. And yes, and to come back to our information retrieval and supervised learning discussion too, I personally, one of the systems that first caught my attention was CoSearch from Salesforce Research. And this was around, this was during peak kind of COVID-19 hysteria, where we're trying to look for whatever application deep learning can be used for. And one of the most interesting ones was scientific literature mining. And so there was a lab, I think from Johns Hopkins and other people, they tried to build a labeled question answering data set, but they were only able to get like 124 pairs in 23 hours of their work quickly, this rapid scramble kind of thing. But so they weren't really able to build a big data set that we were used to using with deep learning. So we're looking for these information retrieval components, and CoSearch was this system that said, here's our vector index, here's how it flows into a re-ranker, question answering, abstractive summarization, all these different tasks. And you see how all these different components kind of flow through one another and build this kind of complex system where the modularity of being able to replace these different components is so interesting. And so we've seen also some really exciting trends in information retrieval, like supercharging supervised learning. I think most recently, well, we'll talk about the most recent one, but DeepMind's retro model is an exciting example where they released two language models, this Gopher 280 billion parameter model, and everyone says 280 billion parameters, wow. Then they're also saying here's retro. If you add the information retrieval, it's better because it has the context better. Yeah. It makes a lot of sense to have the context. So then kind of coming into the most recent thing, and I think transitions really well to Weaviate and this idea of computer intuition as we talk about how you use these kinds of search engines and then how machines use these search engines. To me, it started off, the first paper I became familiar with was Facebook AI researchers had a paper titled Internet Augmented Generation, where they're querying the Bing search API to do the information retrieval. So it's not querying a vector search index, it queries the Bing search API. And now today or yesterday, we have OpenAI's WebGPT, where the same idea, you query the Bing search API, but similar to what we're talking about with computer intuition and how you use search engines, they're using reinforcement learning to train the model on how to interpret the results of the Bing search API. So what Weaviate lets us do is we have our neurosymbolic search. And again, coming back to this idea of serendipity, symbolic filters, traversing graphs, the models can learn how they're going to really query this search API. So they can, do these things like question answering and then learn how to use their information retrieval component, which is something that I see as being such a powerful supercharger of this.
Yeah, no, I agree. And I think so. What's interesting about what you're saying right there is that from a research perspective, I completely get this, right? Because you try to solve a problem and then there's the Bing API to give you these results. But if we look at one, there was also one of the eye openers that I had. That was like, if we would live in a world where all data would be publicly available, then there would be no room for existence for something like Weaviate, because you just go to Bing or to Google and you find anything, right? So the idea is that I had was like, so how much data are we talking about actually? So how much data is behind closed doors and how much data is actually publicly available? And Microsoft and Google are quite open about how much data they have in their search engines. And then if you look at estimations about how much data there actually is in the world, you get to a number of like 0.0001% of data that Google actually has indexed. I mean, I might be a decimal point off there, but the point is it's far less than 1%. So that we thought like, hey, wait a second. So you have the data, you have the models, but you also need that search engine if you want to apply this to your own data. So if you're a bank, if you're an insurance company, if you have a startup that's generating their own data. And that is what plays so well together with these existing models that are trained on this the information that's publicly available. And I think one of the things that I often am in discussion about with people is the whole concept of fine-tuning, right? So, and that I say, I understand the academic argument for saying like, in theory, for every case, you need to have a fine-tuned model. I get that argument, but in practice, how people use it, these general purpose models already bring them the results that they need. And I think that based on these examples that you just gave, Connor, I think we will see more and more of these general purpose models, as I like to call them, being used by more and more people because they are already giving them the results that they need, even if they are trained on stuff or getting the results that are coming from the Bing API or whatever they're coming from, right? Or the common crawl or those kind of things. So I think the point that I want to make is that I think like a trend that I think that I see in the usage of these models is that because these models become so much better over time, using them for general purpose use cases becomes easier and easier as well. So you need to do less. You don't need a PhD anymore, basically, to use such a model for your business or what have you.
Yeah, I think. Okay, so I'm going to push a little back on the abandoned fine-tuning idea. And
I thought you would. So yeah, bring it on. Yeah.
So I'll go through a list of citations, and the first of which is "Don't Stop Pretraining." It was one of the ACL 2020 Best Paper Awards, where it says, basically they set up their data set of you have news articles, IMDb movie reviews, biomedical papers, and computer science papers, and they showed how continuing the pre-training for the domain of interest is extremely useful. But I think, and I do agree with this idea that foundation model, these bigger models on more data are more generally useful. But so I think the next paper that we can kind of learn from is, I think it's the Allen Institute, WiseFT. I've made a video explaining this paper on my YouTube channel if interested. And what it is it shows this relationship between these large pre-trained models and then these fine-tuned models with respect to in-distribution accuracy and out-of-distribution generalization and flexibility. So if you fine-tune the model, basically, and the algorithm is that you fine-tune the model and then you have a weight space ensemble along the path from the fine-tuned model from the original starting point. So I think that is going to be a very successful way to trade off the out of distribution, the generalization, the flexibility of these large pre-trained models. But then you also want to have, your in distribution kind of fine-tuned nature. And I guess generally as a PhD student, it does kind of break my brain, the idea that some kind of general model could be better than, fine-tune on a particular data distribution. That idea doesn't really make sense to me, but I guess it.
Yeah, let me try to pitch it to you, right? So what the idea is, what's happening there. So let's go back to that example that I gave of that we were searching for what was Michael Brecker's first saxophone, right? So with this out-of-the-box model based on a Wikipedia data set, we do not find the answer. So from an academic perspective, if you have defined your research as, can I find an answer to a natural language question based on this data set? It would say no, because it's not there, right? The answer is not there. However, if you then take off your science hat and you put on your engineering hat, you can say like, well, wait a second. The answer was actually in the top 5 results. It just wasn't the first one. So if I now run these 5 answers to the Q&A module, and I see what the highest certainty answer is there, then I do get the right answer. So you can engineer your way to getting the answer. And what I'm trying to say is, yes, I agree that in the ideal world that is solved on the academic level. However, the models are already good enough to solve it, to solve people's use cases, solve the questions that people have. So I agree with your remark. You're absolutely right. But I'm looking at it from a different perspective. I'm looking at it from the perspective of, is the model already good enough to solve the problem that this person has? And the reason why I'm talking about these, and I'm doing this, I'm saying air quotes when I talk about general purpose models, is that we see that if you engineer your way out of it, these general purpose models actually can perform better, not on every use case, of course, but on news articles, products, those kind of things, than if we extra fine-tune it on these on specific data sets. Of course, fine-tuning is always better, but that's not always an option. So I'm trying to say, like, what I love to see is like that you have like the scientific side and the engineering side, and they go hand in hand, and they help each other to have these end users build, well, whatever they want to build with these kinds of databases and models combined.
Yeah, so my take on the engineering solution, and thanks to Dr. Mohit Bansal from the University of North Carolina for sharing this paper with me and helping me think about these things, is so their recent paper is VNL adapter. So we're setting things like compactor, adapter, high performer. These are strategies for how we can fine tune clip while only really tuning 4% of the, so particularly this paper, they only need to fine tune 4.4% of the parameters of clip to still retain the full performance as if you fine tune this whole model. So from the engineering perspective of that headache of trying to store the thing and do that fine tuning thing and all that kind of stuff, these compact adapter layers are definitely pushing that in the right direction. But then to kind of come back to one thing that I was curious about in this idea when you mentioned that like the answer isn't in the data set the foundation model was say trained on. What do you think about say your goal is the Weaviate documentation, right? So you're training a question answering system on the Weaviate documentation. Then I think you need some fine tuning, right, to navigate the Weaviate documentation because it hasn't seen that data before.
So yes and no. So yes, it always makes the results better. But again, so we need to be clear about what we define what the right answer is. So I define the right answer is like, can we algorithmically get to the right answer in a decent amount of time, which is different than does the model directly produce the right result? And so if you go for the latter one, then the answer is yes, you must fine tune it. If you go for the first one, then you don't necessarily have to fine tune it. It will yield better results, but you don't necessarily have to do this. And I know that I'm throwing a rock in the pond by saying this, but the point that I want to make is that is actually a very optimistic point, is that these models are already so good that they are helping a lot of people already. And yes, making them better everybody will benefit from this. But let me put it like this. So the other day, so a metaphor for this, right? So the other day I was making a risotto, and I have like certain ingredients that I have in when I make a risotto. So I was getting the stuff, and then I wanted to have a specific type of cheese. So I I'm in a store and I wanted to buy the cheese, and the guy's like, we're out of this cheese. So now the question is like, so from a air quotes academic perspective, I can't make my risotto anymore because I need to have this cheese to go in a risotto. But if I put on my engineering hat, it's like, so what do you have like similar cheeses? And the guy like, yeah, if you use this kind of wine, you can use this kind of cheese as well. So I couldn't make my risotto as I originally intended. But from an engineering perspective, I just used a different cheese, and the people who ate the risotto still were happy with the risotto that I came up with. And that is what I meant, is that I am very interested in how can we get these models and the things they can do with them through the database into the hands of as many people as possible. And part of that comes with the engineering around it and saying like, hey, these models are, so sentence BERT, for example, so many people are benefiting from that without touching the model once because they don't know how to do it, right? So they go like, I want to build this cool app. I want to build a cool solution. I'm building a website or whatever. And I just want to use that model. And they go like, wow, it works. So all the kudos to the team that worked on sentence BERT. But I want to make this optimistic you point them say like, so it's already bringing so much value to people, even though from an academic perspective, it can still be better.
Yeah, definitely. I think we're definitely on the same page with the two different kinds of, like, most applications. Yeah, like right out of the box, the sentence BERT is so great and it's so interesting if you have that human intuition. And then on the academic side, as we look at things like what DeepMind is doing, what OpenAI is doing, and our creativity goes crazy, and we think computer intuition, the computers are going to be able to do all these tasks end to end, and we get so excited about that idea. And then I think we think about two different ways of using Weaviate, where on the left hand, for where you have some use case and you have the human intuition already, the end-to-end system is good. Whereas I think on the other side, you're looking at the Python client, the API, and how you can put that into your into your training workflows and do research with it, because it's a really exciting research platform. Weaviate is like a product, and it's like a science platform. The science platform is really what excites me a lot, as coming from my background. And so I think to transition, let's talk about the demos that we have and the APIs that are available for the demos and how this enables this kind of research. So with the demos, we have Wikipedia and Wikidata. And can you talk about your conversations with Wikidata and how exciting that's all been?
Yeah, that is fantastic, because the Wikidata, it's actually a funny story, because I found this repo from Facebook research or Meta research, one of the two, but where they had this big graph data set that they trained on Wikidata. And so one of the things that I constantly do is that if people like something that they're seeing, I want to know why. So I asked them, why do you like this? So what we noticed was that we did a demo data set with Wikipedia data and with Wikidata. So the Wikipedia one was just interesting for people to see this at scale. They love it. They mostly engineers, or as I like to call them, tech-savvy product managers that play around with the API and they go like, oh, this is great. I want this in my solution as well. But the big graph one was another one. So somebody was very enthusiastic about this, and so I said like, why? And this person told me the following. He said, so we do the research, we generate the model, and now we have many gigabytes of vectors and the wiki entities related to it. And we're gonna kind of assume that it works, because how are we gonna test that in practice? Are we gonna load all these things in memory in a Python script and search through it on our laptops? No, we don't, because it's not practical. He said, and what you did with Weaviate is just you were actually showing in action how it works. Mm-hmm. We could actually try out this model that we were so enthusiastic about. And that was such an eye-opener for me, because that step, this proved that step that I always say, like, you need in this new ML first world, right? So you need the data, you need the models, but you also need the database to search through it. And we got so much positive feedback from the folks. Even on Wikidata, we were like the tool of the week. And then you go like, oh, this is amazing, because people now actually they can work with it, they can play around with that. And we're definitely gonna do more work on making that data set better. We're just gonna keep that completely open source for people to play around with it. I even already know about people who reached out to me that are changing it. They forked it and they're changing it to build it even in their own solutions and their own products. And I was like, yes, that's exactly what we want. And I hope that that early next year I can share some more cool things about this as well.
Yeah, it's so cool seeing the graph embeddings and really looking through graph embeddings. Wikidata is probably the best example. Maybe like if we constructed a Twitter graph where it's people who follow you and then your nearest Twitter neighbor or something like that would be another way of seeing these graph embeddings in action. Because when you pointed me in the direction of PyTorch Big Graph, that was really the first time I'd really looked at PyTorch Big Graph. Do you have any other kind of like examples of graph embeddings that inspire your excitement about these kinds of ideas like Wikidata graph embeddings?
Yeah, so sometimes the ideas come from data sets that I see, sometimes the ideas come from the models that I see. So I was immediately intrigued by a model which is called Cybert. And Cybert it vectorizes cybersecurity logs. And bear in mind, so what the problem there is. So the problem is that if something comes from like a weird IP address, you can immediately block it. But if something else is happening that you can't solve algorithmically and a human needs to look at it, that's an opportunity to do something with these embeddings. So people started to create embeddings based on cybersecurity logs. And I was like, oh boy, that's amazing, because now you can store all these logs in a Weaviate. And if new logs comes in, you can do a similarity search on threats from the past and say like, is this somehow related to each other? So that's just one idea. Another idea that I had was the tremendous amount of work that I see happening, for example, gene2vec and those kind of things. You can easily store a human genome in Weaviate with its vector representations and search through it. I would love to do some work there as well. So we have genes, we have same goes for proteins, but also customers, right? So you have a customer that behaves in a certain way. You can create an embedding based on these graph embeddings for this customer. So now you get all your customers in a Weaviate and say like, how are they related to each other? The graph relations that people make are amazing. So for example, I saw an example about like hotels and people. So where you can say, okay, I have like Connor and I have Bob, right? Bob booked hotels, Connor booked hotels. Now we get like John Doe in. And John Doe books one hotel or behaves in a certain way. So the embedding that's created for John Doe might gravitate towards you. So then you know, okay, let's also show the hotels or the types of hotels that Connor is interested in, opposed to the ones that Bob is interested in, because this person behaves in a similar way that Connor is doing. And this can go very far. We're not only talking about the hotels that people booked, but even how they search through the website, where they click on and those kind of things. And what we also see, and now I go a little bit away from the embeddings, but something where the embeddings are used, is that there's this whole thing happening with privacy and like a post-cookie world. Here, embeddings help as well, because now you can create an embedding about somebody without knowing who this person is. So it's very privacy safe, if you will, but you can still give a great user experience for whatever tool you are creating based on the embedding that you are creating for this user. So it's just, there's so much happening. That's just fantastic.
Yeah, graph structured data representations is such an exciting idea. And shout out to Zach Jost at Welcome AI Overlords, is his YouTube channel. And he's working on this problem of like fraud detection, cybersecurity, and how you can make it a graph structured problem. Really interesting idea. And all sorts of content about graph neural networks. Graph data is kind of the most natural way to represent some kind of data. And the biology, the protein-protein interaction networks, the drug target, drug repurposing being like the big application sort of to look at. All these kind of graph structured data is so interesting. When I first was looking at graph structured data, I was thinking in this context of like system 1, system 2 kind of thinking back when that book Thinking Fast and Slow came out, and that was kind of an exciting idea in deep learning research. And so I always thought of graph structured data as being like the system 2 component and kind of like causal inference, like the way that we, if we talk about information retrieval and then supervised learning being like system 1 is information retrieval, system 2 is supervised learning, reasoning, say. I always thought graph structured representations would be limited to that second part, but now I'm seeing more how graph structure can help you build the embeddings of the data as well as sort of like raw text representations. So one kind of question, and if we can just pass this if you haven't thought about this, but I was thinking about like, how do we combine the Wikidata graph structured embeddings with the Wikipedia text embeddings? How do those two things play together?
Oh, well, actually, I love that question because I do have some thoughts about this. So One of the things that we have within Weaviate, and that's on purpose, is that you don't choose a model to attach to a Weaviate. No, you choose a model that you attach to a class that's in your Weaviate. So you could create a Weaviate that has like the paragraphs from Wikipedia with the sentence bird embeddings, but you can have another class in there that represents the Wikidata, and that you say like, okay, we're going to use the big graph embeddings to store that in the same Weaviate. Now you might say like, well, but they are in completely different vector spaces. That is true. That is, but what you can do, for example, is that let's say that you somehow start from the perspective of the Wikidata, the big graph embeddings, and you traverse the graph and you end up with Stanley Kubrick, as I always like to give as an example. And now you say, okay, I want to now know more about this director. Then you can just do one simple query and say, okay, I found this Wikidata node in the graph. Now jump to the most similar a node in the part of the Wikipedia embedding, the sentence embeddings, and that is they are not closely related from a embeddings perspective because they're different embeddings. But you can do the query, so you can say, oh, I know from the Wikidata that it's a director with the name Stanley Kubrick, and then you can do the semantic query that's handled by the sentence bird model to find it there. So you can jump back and forth in that graph, and that's really what's solved in the database. So I would even dare to go a step further. I think that a year from now, we're going to see more and more use cases where people have like 4 or 5 models just zooming in harmony in one Weaviate instance.
Yeah, wow, that's really exciting. And I think from here we'll transition to multimodal learning and getting into this idea of 4 or 5 vector spaces and combining the vector spaces. But just quickly before we transition to that, I also wanted to just, again, like there's Wikipedia, Wikidata, and I think another problem that might motivate listeners into doing this research is scientific literature mining, where you have citation networks and then you have, say, the text embeddings of the papers. I think that's another very inspiring kind of application domain. I see so many scientific literature mining tools out there and people tackling this problem because I think it's a really fun way to think about it and build a research career around these kinds of problems. So let's talk about multimodal learning. And, we're talking about combining vector spaces with queries, with class references. We're talking about the GraphQL kind of structure between different things. But let's just kind of start with like the image text and the idea of the clip in the V1.9 from Weaviate and how we do image text search and connect it to all these kind of exciting ideas.
Yeah, so there are 2 things that I think that are interesting to say about this. So the first is using multiple models, like for example, clip and sentence embeddings in one Weaviate. I will talk about that in a bit. But the second thing is that I wouldn't be surprised if at some point, and this is out of my realm of expertise, but I would not be surprised if at some point somebody steps up and says like, hey, wait a second. We can make relations using Weaviate as the search engine between 2 completely different models. So for example, the big graph model and the sentence bird embeddings for the Wikidata. I can say something about their distances by having a natural language query in between. I'm going to train a new model that is going to try to predict these relations. I would not be surprised if we see that happening. And if anybody's listening to this podcast who wants to do some kind of a research project around that, then they should reach out to me. But to the first thing, what we see a lot is this. So sometimes you have use cases where you somehow want to mix image search and text search, but also different types of model search into one. So we see people create multiple GraphQL queries. And then you have something which we like to call the business logic layer or the middleware layer, where they do something with these results that they're getting back. Because sometimes somebody might, let's say you have an e-commerce solution, somebody types in natural language what they're searching for, but on the page that is being presented to the end user, you might want to have natural language results. So there the products come to the sentence embeddings. But maybe you want to have an overview of 3 products that are similar to the image of the first result, or images that are being returned based on the natural language input. So then what happens is you have like a e-commerce front end, somebody types in a whatever they're searching for. In Weaviate, we do a sentence embedding search and a clip search. The sentence embedding search returns natural language results, so that can be product descriptions, reviews, but the clip results return images. And then people do super cool creative things in actually showing that to end users, how they can find the products that they're looking for. So that's a little bit different to your question about like those multi-models. But what I meant is more that it sparks a clip, for example, gives people the capability to now go from a natural language to the image, something they couldn't do before. And they built very cool things with that. And so the more of these types of models we see, I don't know what people will come up with, but going from doing something with video or with audio or those kind of things, our users benefit from that again, because they get more capabilities to get to potential results in these search results. So that serendipity that we talked about earlier, to present that to their end users and use these models in practice. So it's not 100% answer to your question, but it's more like an example of how these new models like Clip are being used and what we see people build with them.
Yeah, and it's so exciting, like how it really enables that kind of like turning, say, Instagram into a like a standard kind of e-commerce platform. Like if you imagine the way that, say, like I shop for Nike basketball shoes, I just look at like the standard shot where they're like centered in the white background and they're like right in the middle. Imagine to like wanting to see like what do they look like on the court? Like what do some players wearing them look like? And that kind of search and doing that kind of nearest neighbor where you take this little static picture of them in the shoebox and then you go see what does it look like in action, so to say. And
that is a super, sorry for quickly interrupting you, but I love this example because that is exactly the example where you have multiple models in the database zooming, and just constantly creating these vectors, but that allows you to create these kinds of applications. And exactly the example that you just gave was hard to achieve, if not impossible, without Clip. But now with Clip, you can do these kind of things on the fly. So that's nice.
Yeah, and Clip has to be in like the top 10 breakthroughs. It's such an exciting kind of thing. It definitely is.
Yeah, so, no, I agree.
Yeah, and then so just like two other things I wanted to just touch on. It's kind of like just image nearest neighbor search, but also with the metadata annotation. And coming back to neurosymbolic search, where we're talking about text neurosymbolic search, which is kind of obvious because you put the regular expression, so to say, and then it's in the original data point. It's not really like metadata compared to, say, when you have an image and then you have the metadata. So to give an example of what I'm working with the COVID-19 convalescent plasma therapy thing that I mentioned earlier, we have chest x-rays and we want to, it's kind of like this idea of precision medicine enabled with vector search, where we want to try to find like the nearest patient who had a similar experience to you and kind of what treatment worked for them, and search through these large databases and see, how we can customize your treatment, so to say. So when we're searching for nearest chest x-rays, maybe that's something we're interested in, we could add the metadata, like whether you're a cancer patient as well, whether you had some kind of pre-existing heart condition, and that kind of information would be really useful for interpreting these kinds of medical images and that kinds of idea. And another interesting idea is this new data set that's being led. It's tons of researchers, I think Stanford, Berkeley, I don't know the whole list because it's a very long, it's one of these papers with like 20, 30 authors on it. Yeah. But the data set is called Wilds. And so what Wilds is it's about annotating data for the sake of measuring domain generalization. And so we have this kind of additional metadata annotations on our image data sets, our molecule data sets, our text data sets, and this metadata that you can integrate through this GraphQL interface. That's what I think really brings home neurosymbolic search. And that's kind of one of the things that really has excited me so much about this and helped me keep my interest on this particular idea. So I think we've covered so many topics and about like the technical ideas and these visions for the future, but I think a lot of people out there would be curious about like your journey as a CEO, co-founder of Weaviate, and recently featured in TechCrunch, and kind of like, so what's your experience like with building this out as a company and your vision for the future on how this kind of game is played, so to say?
Oh, where to start answering this question? So so first of all, it's like the joy that you have if you see like downloads going up, positive feedback that you're getting, that is fantastic. And what you said about the TechCrunch thing, etc., that's just amazing. And that just is proof of showing like, hey, there's actually stuff happening in the world. People, the mindset of people is moving towards using these vectors in production. And one of the things that is my personal goal is to have these things like, for example, the research that is happening. So that's the knowledge that people like, for example, like you have, the engineering that is happening. That's the knowledge that, for example, HN has, the user experience part of it. So that's, for example, knowledge that Lara has. My role is combining these things together and figuring out how that helps people on a day-to-day basis, right? So the example that you gave about the medical use case, right, with the X-rays, we know, unfortunately, I can't say much about it yet, but we have these kind of cases as well. The most beautiful thing is if you sit with a doctor and you show the first results, and this person who is like zero knowledge about how it works says like, this looks great. I see where this is going and I like it very much what I'm seeing. That is like in the journey, that's the most beautiful thing. And every week I'm uncovering more and more of these cases. So that is one of the things that I'm very excited about. Like, I keep just being surprised how big the opportunity is. There's like, I haven't reached the limit yet. So that's one. And the third thing is like, some people who have looked at Weaviate might have seen some hints about it already. And that is, if you find a node in the Weaviate graph, it has its own scheme created to it. So it's like you see Weaviate, colon, / localhost / and then you find the node in the graph. Well, the fact that it has localhost there assumes that in the future it can maybe be something else than localhost, so that it can be somewhere else over the internet. And one of the things that is my personal big dream with this, if this keeps growing, is that the big problem that we talked about earlier about the semantic web and how do we connect these things together, is that you can actually say, well, let's say that I have a dozen Weaviates or 10 dozen, Weaviates spread over the world, and I just spread a query over the network. And I let these models solve the answer and return the results. So a very simple example, let's say you have a Weaviate from the New York Times and you have a Weaviate from the Wall Street Journal, and somebody says like, okay, what's happening now with COVID? You shoot it over the network and both of these Weaviate instances return the results, and you can in GraphQL represent them to the end user. So you get like as I like to call it, a knowledge network. And that is something that I'm really excited about these kind of things as well. Doesn't exist yet, but if you look at Weaviate, you see all the ingredients already being there, which is just allowing people to connect data sets together, to connect knowledge together, to connect insights together outside of one instance. And that is something that I'm also super excited about. So that would be my answer, I guess.
Yeah, that is an exciting vision. I really like that. like with Hugging Face Spaces, and big thanks to Merv and Omar for helping me with my personal experience of setting up my Keros BERT with Henry AI on Hugging Face Spaces. They're building up all these demos of deep learning models, and it's all in one central thing. And imagine putting all the demos of Weaviate and then you build a model on top of that, and that's exciting. Yeah.
And that is the beauty, of course, of the whole open source nature of it. So the Hugging Face has that, we have that. It's like, it allows people to work together and build these amazing things. And back to your question about like what my role, the only thing that I need to do is actually just make sure that these things resonate in harmony. That's what I do. So other people do the hard stuff. I just try to make them resonate in harmony. And well, some people might argue that that's another for another podcast. But and that is just amazing to see how that works and how enthusiastic people get about it. And that's just, I wouldn't be surprised if this goes X10 next year, right? So that's just fantastic.
Yeah, it's amazing. I mean, like, you're definitely a visionary. You see these things ahead, and I think that's really exciting to be learning from you about that. And yeah, that idea just then was so exciting to me, and all these things. So So thanks so much, Bob. I'm sure we'll do more of these podcasts on our Weaviate Semi-Technology podcast. I think this was a really great one. Thanks again for doing this with me.
No, thanks also for having this conversation with me. And it's always great to talk to you, Connor. So thank you so much.